So now let's go back to our octave again. We will now look at exercise number 16. So exercise number 16, they give you two field force, that is F1 and F2. And 16a, they ask you to look for the conservative force. So if you remember what is the definition of a conservative force, you will know that you have to evaluate the curl of F, and it should be equal to 0. So between these two forces, if you evaluate curl of F, you will find that F1 is a conservative force. So in this short video, I'm just going to show you how to plot the vector field using two ways, that is from this equation explicitly, F1, or in the case where you do not have F1 but you are given the potential, and you can also get the same vector field. So let's look at the first way, that is using this explicit equation. As usual, the I component, we will define it as U, J as V, and the K component as W. So let's go to octave now. So this is the picture that you will see when you plot, but let's just close this one first. And let's clear the command. As usual, let's go with the X. We define the points in the X direction. The same, we will define the points in the Y direction, and as well as the points in the Z direction. And then you will have to define the mesh points using this mesh grid XYZ. And then you will calculate what is the I component, that is U. U is equals to 2 times X. V will be equals to minus 2y times Z, and W, it is equals to minus YY squared, YY squared. So once you have do this all these calculations, then you can use the quiver tree. So here you have to be careful, X, Y, Z. So this is U because this is the I component, V for the J component, and W for the Z component, or the K component, sorry. So now you enter, and you will have this plot. Right, so let's let me just put the label. So X label, Y label, and Z label, and then you will see this is the plot. So now maybe the first thing that we should ask ourselves is whether the plot is correct. So there are many ways that you might want to check, but here there is one simple way. So if you look at the equation here, the K component must be equals to negative Y squared. So it doesn't matter what is your value of Y, be it negative or positive, the component is going to be negative value. So it means if you just imagine your vector, it is going downwards on your Z axis. So now if you go and look at your plot, you will see this is my Z axis, and over here this is my Y axis actually. So here you will see the vector is pointing downwards. Okay, so this gives us confidence in our plot. So let's look at this is XZ direction. So XZ direction, it looks like this. If you turn it a little bit, you have the Y axis, XY plane. So this is your XY plane, and if you turn it, you will get your XY plane like this. So just have to turn it. Okay, so now this is my X, this is my Y. So here you see the vectors are pointing on, here is pointing towards the right, and here this is pointing towards the left. Okay, so this is the vector field that you obtain by plotting the F1 explicitly. So now what happens if you try to plot using a potential? Okay, so the answer to this potential, if you have done the exercise, it is equals to x squared minus y squared times z. So let's now define phi equals to xx times xx, because it is x squared, minus yy times yy, because it is y squared, times zz. Okay, so this is my potential, and now I have to find the gradient of this potential. So let's define first dx equals to 0.1, dy equals to 0.1, and dz equals to 0.1. Now I will find the del x, del y, del z, and this is equals to gradient. The first term over here, this is the function or the potential that we want to take the derivative. This is dx, this is dy, dz. So now let's enter. So now if you want to plot this, you will have again to use the quiver tree, but instead of UVW, you will change this to del x, del y, and del z. And voila, this is your vector field, which should looks exactly the same as you got just now. So now what we can do is we try to superimpose this plot with the plot that you obtain from the explicit field equation. So we type hold on, and then we plot quiver, the one with the UVW. So now you will see there is two colors to it. So let's just change the font size and the label, Y label now, and the Z label, and now we look at the plot. So this is it. So over here you can see there is two color, one is in the blue, which is the first one, and one is in the green, and you will see that they are exactly the same. Okay, so here we have managed to plot the vector field using two ways. One is by using this equation where you define this is UVW, or in the case where you do not have this field force, but you have the potential. So when you have a potential, by definition you have a conservative field, and you can try to find the vector field from this potential. Right, so basically I'm showing this so that you might want to consider using this kind of a software to make a plot and to check, your answers, whether the one that you obtain from your calculation is correct or not. Okay, so basically that is all for now, and I wish you all the best if you want to play with this Octave or any other plotting software to plot the vector field.